the assumptions. What's the conclusion? What if you change the assumptions? How does it relate to other theorems? Can you draw a picture? Does it work for simple cases?
Lots to chew on for each theorem.
And generalization. Always ask, can this be made more general? That's a huge driver in math. Finally, a proof is just a convincing argument for why something is true. But importantly, the way a proof is written is often very different from how it was discovered.
The polished version hides the messy journey.
Often, yes. And the main proof techniques are listed: direct, cases, contradiction, induction, contrapositive.
Which leads nicely into actually reading and understanding proofs. The motto is nullius in verba.
Take nobody's word for it.
Yeah.
Exactly. You have to convince yourself. Reading a proof is like unpacking something tightly bundled.
So how do you unpack it?
First, rewrite the theorem statement yourself. Clearly separate the given assumptions and the to prove conclusion. Then, as you read the proof step by step, pinpoint exactly where each assumption gets used.
Okay, track the assumptions.
And try applying each step to a simple, concrete example. See it in action. Check every claim. Look up any theorems they reference. Don't just trust it.
Be skeptical. And testing with extreme cases.
Yeah, like if a theorem involves variables, what happens if they're 0, or equal, or very large? Also, try the proof logic on a non-example. Where does it break down? Like trying the Yusu irrationality proof on 4, where does it fail?
That would show why the proof works for Yusu specifically. Smart. And reflect. Have I seen a proof like this before?
Right. Recognizing patterns in arguments is key.
Okay, so let's look at those proof techniques in a bit more detail. The direct method first.
Simplest idea. Assume the hypothesis is true and just use logic, definitions, previous theorems step by step until you reach the conclusion. The book shows an example proving one fraction is bigger than another.
Right, the m plus 1 millimeter one. It shows the messy discovery bit first, then the clean, polished proof.
Exactly. It also covers common direct proof tasks, showing two things are equal, often by manipulating one side to look like the other, or showing their difference is 0. Proving if and only if requires proving both directions of the implication.
Like 2 proofs in one.
Essentially, yes. Or sometimes you can use a chain of reversible if and only if steps. And proving 2 sets are equal usually means showing each is a subset of the other.
Mutual inclusion. Got it. Any common mistakes in direct proofs?
Biggest one is assuming what you need to prove. Circular reasoning. Also, using implication arrows wrongly, like thinking AB means BA, and of course, dividing by 0 accidentally.
Always watch for division by 0. Okay, what about proof by cases?
Sometimes called exhaustion. You break the problem down into all possible distinct cases, and then prove the statement is true for each separate case. If you cover all possibilities, the statement must be true overall.
Like the examples, showing no plus 3n plus 7 is always odd by checking cases for n even and n odd. Or nn is always a multiple of 3 by checking n mod 3 cases, 0, 1, 2.
Exactly. If the cases cover everything, you're golden. Then there's proof by contradiction, a really powerful, sometimes mind-bending technique.
How does that work again?
You want to prove statement P, so you start by assuming P is false. Assume not P. Then you use logical steps to derive something impossible, a contradiction, like 1, 0, or x is both even and odd. Since your assumption led to nonsense, the assumption must have been wrong. Therefore, P must be true after all.
The classic example being the proof that Chinese is irrational.
The absolute classic. Assume shu is rational, PQ in lowest terms, square both sides, do some logic, and eventually show that both P and Q must be even. But that contradicts the lowest terms assumption. So the initial assumption, 2 is rational, must be false.
It's elegant when it works. So the steps are: assume the opposite, derive a contradiction, conclude the original must be true.
That's the essence of it. Next up, mathematical induction.
Right, this is for proving things about all natural numbers usually,
Yeah.
like sums or sequences.
Often, yes, or anything indexed by integers starting from some point. It's like setting up dominoes.
Yep.
2 steps. First, the base case. Knock over the first domino. Show the statement is true for the starting value, often n1. Second, the inductive step. Show that if any one domino falls, if the statement is true for some arbitrary number k, then the next one must fall. It's also true for k plus 1.
So base case plus inductive step implies it's true for all numbers from the base case onwards.
Precisely. The book uses it to prove the formula for the sum of the first n numbers, 1 plus 2 plus n plus 1, 2, and the sum of the first n odd numbers equals n.
Nice examples. Are there variations?
Sure, you can start at n0 or n by 5 or whatever the appropriate base case is.
Mhm.
Sometimes you need a stronger inductive hypothesis, assuming it's true for all values up to k, not just for k itself. Induction is incredibly powerful. It's used to prove things like the fundamental theorem of arithmetic, unique prime factorization.
Wow, okay. And the last technique mentioned, proof by contrapositive.
We touched on this. To prove if A then B, you can instead prove the equivalent statement, if not B, then not A. Sometimes proving the contrapositive is just easier, algebraically or logically.
Like the example. Prove if x is even, then x is even. The contrapositive is if x is odd, then x sets is odd. And proving that is quite straightforward.
Exactly. Sometimes switching to the contrapositive just cleans things up nicely.
Okay, that covers the main proof strategies. The deep dive then uses number theory for specific examples.
Yeah, applies these ideas, starts with divisibility, A divides B, written AB, presents theorems like if AB and AC, then AB plus C. It actually walks through the messy thinking versus the final polished proof for that one.
That's useful, seeing the process.
Very. It discusses corollaries, like if AB, then AB, and reinforces that the converse of a theorem isn't automatically true. Just because AB plus C doesn't mean AB and AC.
Right, need examples to show converses can fail.
Then it introduces the greatest common divisor, GCD. Explains the Euclidean algorithm, that neat process for finding the GCD without factoring.
That's a really useful algorithm.
It is, and it leads directly to Béziers identity. You can always write the GCD xy as a combination kx plus evenly for some integers k and l. That's fundamental.
And that connects to Diophantine equations, those linear equations where you only want integer solutions.
Exactly. Béziers tells you when x plus by xcc has integer solutions, it's if and only if GCD AB divides C. Then it moves into modular arithmetic, x, a, y, bod, n, its properties, and Fermat's little theorem as a cool application.
So lots of concrete number theory applications. What about functions?
Key concepts there. Injective, one-to-one different inputs give different outputs. Surjective, onto every possible output is actually hit by some input.
Yeah.
And bijective, both injective and surjective.
And rejections are the ones that have inverse functions, right?
Correct. If a function is bijective, you can perfectly reverse it. This leads into talking about the size of infinite sets. Countably infinite sets are those you can put into a one-to-one correspondence with the natural numbers, 1, 2, 3.
Like the integers themselves, or even the rational numbers, fractions.
Yep. The book shows Cantor's clever grid method to demonstrate how you can list all rational numbers, proving they're countable. But then comes the big shocker.
The real numbers aren't countable.
Exactly. Cantor's diagonalization argument proves that even the real numbers just between 0 and 1 are uncountable. You can't list them all. There are fundamentally more real numbers than natural numbers.
So some infinities are bigger than others. Mind-bending stuff.
It really is. Then the last main topic is relations, focusing on equivalence relations.
Okay, what makes a relation an equivalence relation?
3 properties. It must be reflexive, everything is related to itself, xx, symmetric, if xy then yx, and transitive, if xy and yz then xz.
Like regular equality, or congruence modulo n.
Perfect examples. And equivalence relations do something neat. They partition a set into disjoint equivalence classes. Everyone in a class is related to everyone else in that class, and nobody is related to anyone outside their class.
So like with Mod 3, the classes are -3, 0, 3, 6, needy, 2, 2, 1, 4, 7, and best 1, 1, 2, 5, 8.
Exactly. Those are the 3 equivalence classes, denoted 0, 1, 2. The set of these classes is called Z, so Z3 in this case, and you can actually do arithmetic with the classes themselves.
Fascinating how that structure emerges.
Yeah.
Okay, so finally the book circles back to generally developing mathematical thinking.
Yeah, reinforcing some key habits of mind, like always try reversing questions. If you know how to find the maximum of assertion, try designing a function that has a given maximum. It deepens understanding.
Turning the problem inside out.
And generalizing. Can you weaken the assumptions of a theorem and still have it hold? The division lemma example shows this. Also, the phrase, without loss of generality, double log, a way to simplify a proof by considering only one representative case when other cases are essentially identical.
Ah, that's a useful shortcut sometimes.
It is. The book wraps up with some fun exploration examples, magic squares, a milk crate packing problem, stamped denominations, and gives checklists for understanding definitions, theorems, proofs, the whole shebang.
Okay, wow. That was a comprehensive dive. So, pulling it all together, What are the absolute core takeaways for you, the learner, from how to think like a mathematician?
The book really boils it down to two practical pieces of advice that underpin everything else. First, make a real effort to write mathematics correctly. Second, actively create your own examples.
Writing clearly forces that internal clarity we talked about.
Absolutely. If you struggle to write it down precisely, using proper sentences and logic, it flags where your own understanding is fuzzy. You can't hide from yourself in writing.
And creating examples is where the active learning happens.
That's where the real engagement is. Testing definitions, pushing boundaries, seeing how things work or don't work by constructing specific cases. That's how you move from passive reading to active mathematical thinking.
We've seen those key proof techniques too: direct, contradiction, induction, contrapositive, and how to prove things are equivalent or equal.
Right. Remember, proving equivalence, if and only if, usually needs two separate proofs, one for each direction. And proving equality often involves showing mutual inclusion for sets, or algebraic manipulation for expressions.
So we really hope you, the learner, take some time to reflect on all this. Maybe go back to parts that felt particularly insightful or challenging.
Definitely. It's dense material, but the habits of mind are so valuable.
And maybe a final thought to leave you with. Real mathematical understanding, the kind this book promotes, isn't about just knowing facts or formulas. It's about the process, the questioning, the struggle, the exploration, the joy of figuring things out and creating logical arguments. It's an active adventure.
Well said. It invites you to go beyond the sources and really engage with the thinking itself.
Thanks for joining us on this deep dive.